Hello? Hello. Hi,
Hi,
Thomas.
Mike.
It's Monique. How are
Hi.
you?
Good. Looks like you got everything going. You already got your little screen up. So perfect.
Okay.
Got things under control.
All right. Thanks.
Sure.
So
So,
at 12, I just get started, or
no. What I'll do is I'll have Jim Rickles introduce you, and then after that you could begin. What we're gonna do is hold questions till the end. You present throughout the end, and then we'll either have I'll moderate the questions, and then we'll go from there.
All right. Sounds great. Thanks.
Sure.
I have a run, so I'll be right back.
Monique, we'll probably wait a few more minutes just because there are some late registrations coming through,
Okay. All
and
right.
and also some of the team is still not on, so
Okay. Sounds good.
we'll let you know. Hi, Jim. I see that you're on. We're just going to wait a few more minutes for people to join to sign in. There's been some late registrations.
Yeah, that's fine. And I can introduce Monique, and then you can handle the questions and all the other stuff afterwards. Then.
Okay, thank you.
I'm going to mute, but just let me know when you're ready then.
All right. Okay, we can begin, Jim. So if you want to introduce our presenter for today, and then we'll go from there.
Okay. Yeah, good afternoon, everyone. Maybe good morning, depending where you are. My name's James Rickles. I'm the director of the LEHIGH NERI Experimental Facility. And I wanted to welcome you to today's seminar. It's one of several in a series of seminars. The seminar today is entitled AFRP, and I'll let our speaker define that as she proceeds. But AFRP, reinforced concrete bridge decks and composite replaceable structural fuses as energy dissipators under cyclic loading. And our speaker is Monique Head. She's an associate professor at Morgan State University, but also the associate dean of research and graduate studies. She has a research lab that includes the Green Transportation Infrastructure Center, and that focuses on addressing our nation's deteriorating transportation infrastructure and innovative ways to renovate that using fiber-reinforced polymer materials. And so without further ado, I'll go ahead and pass the podium over to Monique, Dr. Hood, and Dr. Head, and let you go ahead and present there, Monique.
All right, thanks, Dr. Rickles, and thank you everyone for attending this webinar. So for this talk, I'm going to briefly go over a little bit of the evolution of this work and kind of how we ended with the bridge columns. So I'll first start off with the kind of motivation and background, which largely comprised of some work that I had done when I was at Texas A&M University and used these aramid fiber reinforced polymers, which are basically like a Kevlar type of composite bar, and how I use them for a concrete bridge deck, both pre-stressing these AFRP bars and non-pre-stressing them. And with the good performance in terms of deformability, how this then propagated to maybe considering use for columns, and how we are navigating that. So also some of the mechanical properties, the input for the modeling, and the details of a parametric study, followed by the analysis of our results and some kind of talking points and ideas for future work. So as a little bit of background to fiber reinforced polymer bars, in general, composite materials are nothing new, but are gaining more interest, particularly in civil engineering applications. You've probably heard a lot in terms of retrofitting structures with these, either FRP wraps, of things of that nature. But for this study, I'm looking at using them as internal reinforcement to replace conventional steel rebar. So just to give you a little bit of an idea of what we're looking at in terms of a stress strain curve, you would see your traditional reinforcing steel has a clear yield point and is quite ductile for larger than 4 or 5% strains. So contrary to steel, the FRP bars are brittle, they're linear elastic, And we know that that could be a challenge or maybe a shortcoming. However, they have strains in the order of 1 to maybe 2.5%. So we have the carbon, the aramid, which I'm using in this study, again, being like a Kevlar type. So kind of like a middle grade level there compared to the others, and the glass. We have seen that AASHTO has had some documents and specifications for glass fiber reinforced polymers for pedestrian bridges. So things are moving along, but in terms of an industry standard of acceptance. But I'll be focusing on how we're engineering the system and using these seemingly linearly elastic bars, but designing them in the range for which we want them to remain elastic, and then focus and address the damage in other areas for which we're using those replaceable fuses for the columns. So backing up, for the bridge decks, we realized that these FRP bars in general had several advantages. The high strength to self-weight ratio is about 10 to 15 times that of steel. These bars, because they're composite, are corrosion resistant, non-magnetic, and non-conducting. And particularly we've seen with the AFRP bars and the CFRP bars, the carbon, we're noting excellent fatigue characteristics. So if we look just in the quick facts comparably to these bars on average, we're looking at stress levels or strengths up to about 220 KSI, very similar to what we're seeing in pre-stressing tendons, steel pre-stressing tendons. But as we see here, perhaps some people think, or it's really a drawback to have this lower elastic modulus of about 10,000 KSI, but is that enough for what we need for when we're designing? So that's the research question that we're trying to address, where the global challenge that we're addressing is the whole idea of corrosion, right? We know that steel corrodes over time, and one of the ways is particularly with bridge decks where we see de-icing salts and this continuous flow of liquids that aid in the deterioration process. We wanted to look at how we could affect this by using the composite bars internally. So just a little bit diving deeper into the AFRP bars. There's several different types that are commercially available. The AFRP is what I focused on. So as we know, it's a little bit less stiff than the CFRP, the carbon, but stiffer than the glass. Technora is a type that was more fabricated out of Japan. You can see again a lower stiffness there. So we use the AFRP type, and then we can compare it to the steel. So these bars come in different types of round bar, deformed bar, larger round bar, larger deformed bars, even flat plates, and even the Technora actually produces a pre-stressing strand. But for this study, I focused on the AFRP bars that were round. All right, so kind of what led us to this step? Well, I was involved on a TechStat project, which I'm going to use the flip side of the test specimen for the conventional bridge deck, for which I'm comparing my studies with the composite. But the whole idea is in Texas, they were looking at having a monolithic bridge deck overhang with the exterior deck panel. So the idea was, can we make it as one panel to avoid having to construct this 3-foot overhang where worker safety was an issue? But we also see with that, you see in past cases, deterioration from tremendous falling, particularly of bridges in marine environments. So my thought was, well, why don't we just look at these panels, bridge deck panels, but more so in the sense of using these composite bars. So that's what led me, and I'll just give you a little bit of summary of kind of the success and kind of some of the mechanics of what we saw from the bridge deck that was reinforced with the composite bars. So like I said, the TechStat, we had they had full depth pre-stressed panels that were totally of steel. But on the other side, we had just our control specimen. And I then used this control specimen, which I'll compare to my composite case, which I'll show in a minute. So just general specifications. We actually had 2 side-by-side panels, each panel being 8 feet by 9 feet long. So globally, we have 18 by 19 feet, where for this bridge deck, we had a stay-in-place panels, 4 inches, and then we had a cast-in-place panel of about 4 inches with a closure pour throughout. So moving on to what the bridge deck looked like, we just used that side for just our conventional reinforced concrete bridge deck to compare the results and see how well this AFRP bridge deck stacks up. So in using similar dimensions of the 18-foot by 19 feet, what we did was we designed the system such that we had concentric pre-stressing of the AFRPs throughout the deck, which was actually perpendicular to the traffic. We actually had 3 longitudinal beams, and then we actually had 1 closure pour for the seam, for which we actually had AFRP bars that were bent to transfer the shear between the decks. And I'll talk about that because we wanted to make sure we had continuity of the shear transfer across the deck. We also had the same shear pockets as in the TxDOT case, where these shear pockets had these 10-inch by 7-inch pockets for which a high strength grout was poured in for these post-install anchorage to ensure composite action between the deck and the beams. So what we also did was kind of like an equivalent force in terms of trying to figure out how much AFRP we needed. We also had AFRP bars on the top and bottom layers, non-pre-stressed, at about 150 millimeters center to center on top and bottom. So in cross section, you can see we did have steel high strength couplers and threaded rods in the shear pocket to achieve that composite action between the deck and the girders. But you see the concentric pre-stressing strand along the section, and then top and bottom for the non-pre-stressed AFRP bars. And the total bridge deck was 8 inches thick. So one of the challenges that we saw, and we noted even from the previous examples, in terms of constructability, what would the pre-stressing operation be? And then also making sure that between the panels, we had enough transfer that was continuous. So we reconfigured or reconstructed or constructed the bridge deck panels side by side with the AFRP bars shown in yellow. So in terms of pre-stressing, we had a dead end and a live end with a strong back on the dead end. And we were basically pulling with a single hole jack per strand. So basically we would pull on it with a hydraulic, pull on the bar with a hydraulic ram. Then we cast in what we had, a high strength grout into this pipe that actually took about 3 hours to get a full set. So there was a lot of time and a continuous operation there. We did actually, before I transitioned, they actually did a full scale where they actually just did a lap splice with these bars and actually was able to use conventional pre-stressing equipment. So it can be done even in the field, although we just used a single hole jack for just pulling on the AFRP bars. So once we were able to pull on them, pour in the grout into the pipe, lock in the stresses so we can get the achievable pre-stressing tension that we wanted, we locked it in there and then cut the strands. So that took about 3 hours per strand for all 20 of those concentrically pre-stressed strands. Then of course the top and bottom grids were laid with non-pre-stressed bars. So that led to our testing plan. We had essentially 7 load cases for which we followed the AASHTO wheel load, where we actually looked at the trailing wheel loads for the interior span for load case 1. Load case 2 was looking at if the wheel load pad were sitting right there on the seam on the edge, right on the overhang with just a single point load, to really look at basically what an equivalent moment could look like if you were to have some type of impact on the barrier and then converting that into an equivalent moment and then a force of what could be felt there. We also loaded on the edges as well as on the interior side by side for our wheel loads. Then again on the overhang, trailing wheel loads on the overhang, then going back to the corner and then the interior wheel load 7 of a single load. So we had a lot of instrumentation you can imagine. We had one single ram that was applying the load through a spreader beam so that we can mimic our wheel load cases. So moving on, we were able to test the bridge deck, and we really got some results that were very encouraging. So we saw this nice fan behavior. So while the bars don't yield, we were able to come up with essentially a modified kind of yield line theory that we got nice continuity just from mapping the cracks across the seam or the joint there, which is very assuring. And then we actually were able to achieve some nice load deflection curves. This is both when we had it on the load case 5, when we were loading on the overhang, as well as on the interior. And if we were able to achieve or exceed the AASHTO minimum factored load and service load. So specifically, if we just zoomed in on load case 1 on the interior span, what did we learn? Well, we basically learned that seemingly, as hypothesized, that the AFRP bars, or the AFRP specimen, the dashed line is a control specimen from the flip side of from the previous TxDOT project of the reinforced concrete bridge deck. We saw that we were able to achieve very high loads and also get some similar deflections. And moreover, we were able to achieve and exceed the AASHTO maximum factored load. So this led us to also see how, and naturally so, given the lower modulus, the system was still quite stiff, but yet deformable. And it was something that we wanted to take advantage of and move into seeing how it can even expand to columns. So the whole idea was that, is it even possible to design a system that, and as we kind of look at even in terms of displacement-based design conceptually, of having the system to remain elastic, right? And then have those elements that we want to yield, and then have these energy dissipators on the outside of these columns to dissipate the energy, while the internal system of bars remains linear elastic. So as we've seen from previous earthquakes and looking at column damage, we see that bridge structures are the most seismically susceptible typically during an earthquake, since they do provide the load resistant capacity of bridge structural systems. We know that confinement is also a major challenge. So basically taking into many different factors, we were trying to come up with what would be a design of these columns with these AFRP bars that perhaps for low to moderate seismic zones could be appropriate. We also recall that research efforts in the past have also started to look at innovative materials, particularly the detailing and the design of them. And that's kind of what led to this research of looking at what would be the column damage tolerance, and moreover looking at post-earthquake serviceability to reduce eventual cost and repair. We also know that columns are your typical compression members, and it's recognized that the failure of concrete in compression is characterized by the localization of deformations in the so-called localized fracture zone or plastic hinge zone. So the whole thing is, can we replicate this system numerically and then validate it experimentally to really understand this design that we're proposing? So we're probably familiar that, you know, if we weren't looking at innovative materials, some of the alternative solutions to trying to refocus the damage, particularly in bridge columns, would be seismic isolation, various lap splice connections, conventional strengthening using bracing systems, or even looking at post-tension tendons for damage control. So moving towards kind of supporting in some of the studies that we looked at to help us as background information for this design of these AFRP columns, we were looking at various research where they had post-tension column-based connections with Liu et al. In 2008, where they had energy dissipating plate connections, where the whole idea was to ensure the uniform distribution of the tendon strains, where we know that that significantly delays the yielding of the tendons, and to also eliminate the stress transfer to the concrete as the strains elongate over lateral loading. So in this system, they had post-tensioning high strength bars, buckling restrained steel plates, reinforcing plates, and keeper plates, as well as shim plates, where the whole idea for this study was a finite element analysis to achieve a performance-based design approach and validating it numerically with their FE model. Also, we also studied and looked at research done by Kurama et al., where they were kind of taking this whole idea of coupled concrete walls with steel beams, unbonded post-tensioning, and the whole idea that they used was having the post-tension hybrid coupled walls with flange cover plates to delay the yielding of the beams, and having seat angles at the top and bottom to provide energy dissipation. So we also just started looking at just some basic reinforced column analysis in OpenSeas with a graduate student who has since finished here at Morgan with an OpenSeas model to compare the AFRP bars to conventional steel reinforced columns. So we know that we got higher base shear. This is a shear versus deformation from our results. Also in looking in terms of drift, we also got significantly lower drifts in the AFRP bars compared to the steel, which obviously achieved a lot higher base shear. So with that, we realized that we wanted to look a little bit deeper to understand and see if we could design a system for which we can achieve a reasonable design. So with that, we extended this study to improve the damage performance of these reinforced columns by trying to prevent any premature rupture of the FRP bars. So ACI 440 notes that the AFRP bars or FRP bars are not to serve as compression members. So with that in mind, we are limiting the FRP bars as compression members, but allowing them to behave in a manner and in the range for which they do well as elastic elements, and to be able to respond elastically and ensure stress transfer to sacrificial members, which is where we decided to have these mild steel dissipators on the outside of the column system, where the steel dissipators would essentially allow the system to rock as well as dissipate energy, where we're focusing the damage in these secondary elements which are replaceable. And I'll also talk about some of the results. So again, looking at where we've seen damage before, trying to use these AFRP bars internally and to couple with the energy dissipators to see how the system would perform. So the whole concept of the replaceability of the fuses was to be able to evaluate the drift of this rocking column with these internally reinforced columns with AFRP bars. So if we look a little bit deeper, we have quite a bit of steel, these 4 bars on the outer perimeter of the column, and essentially have these, you can think of it as a buckling restrained tube with an inner yielding core of about 1/2 inch and an outer core of about 1 inch. If we look a little bit closer at the details, which we are still refining, this is the first pass of the study of looking at the connection interface, where we have the rocking AFRP reinforced columns. We have a footing that has a square column and a head block that we're actually using to attach the actuators. So the main objective is for the rocking connection is to look at the stability of the column under axial load as well as bending and any possibility of failure of the columns along the cross section above the column foundation interface. So what we see here, we have extended steel bars within the concrete column, fillet wells around the steel plates that then are attached to a core, attached to the actual energy dissipators that are within a corrugated duct that run through the foundation of the system. So if we look a little bit of our mechanical properties, we know that we're just using about 4,700 strength concrete, so no high strength concrete. With typical elastic modules for the concrete as shown, and just using basic properties of the concrete. We pulled the manufacturer's data to resemble and mimic the AFRP bars with 10,000 KSI for the modulus elasticity, and looking at ultimate strains of about 0.02, so about 2% strain. For the mechanical properties of the steel, we're looking at grade 60 as well, and then the yield stress and fracture stress for the plates, and then the reinforcing steel. So for the model, we adopted the Makawa and Qureshi concrete model, for which we were able to model the nonlinearity of the concrete, as well as for the steel, just our traditional steel nonlinear model for the reinforcing steel, and then for the AFRP bars, given that they're linear elastic, using a linear elastic model using the manufacturer data to represent the bars. For the mild steel dissipators, again, it's this yielding core of about 1/2 inch, the buckling restrained tube of about 1 inch, yielding stress 270 KSI, and again, the mild steel is what we use for the confined, and then the mild steel. So for the parametric study for this case, again, comparing the steel and the AFRP, we had several models, and I'll kind of go through the nomenclature of how we selected these, but we looked at several models where the main parameters that we were looking at in terms of design was varying the size of the structural fuse, looking at the various structural fuse effect on the steel columns, also varying the percentage of the longitudinal bar ratio, of course looking at confinement, that is the tie spacing of the FRP bars within the reinforced column. Then the other cases, C1 and C4, are conventionally steel and FRP reinforced concrete, so we'll keep our eye on C4. And then the conventionally reinforced columns are C3 and C8. So in putting all this together, we have this numerical model with this square column as shown, the column reinforcing details with the energy dissipators, 4 of them attached to these steel plates, where again, we're trying to focus the damage in this region. So the idea is that we're just replacing the fuses. So again, a lot of information of things that we looked at, but let's focus our attention for these results mainly on model specimen C4 and C5, where we varied the longitudinal reinforcement ratio at 1 and 1.5%, and a tie spacing of about 5 inches. So for the numerical analysis, I know before we had started with OpenCs, but we ended up going and using a software called Extreme Loading for Structures, which is a finite element analysis software that also enables one to do blast, progressive collapse analysis, virtual shake table studies for seismic isolation, cold form structures, as well as performance-based design, and even multi-hazard. So of course we had to validate just the performance of the software, and just compared our results by replicating a traditional column, a circular column with tendon ducts, based on a study by Larkin in 2004, where the blue shows our numerical study compared with experimental studies by Larkin to validate mechanically and the nonlinear behavior that the model was doing what we wanted it to do. So for the study, there are several factors that we assessed in terms of the global performance of the column, where we're looking to examine the post-peak strength deformation, of course, ductility in the sense of the column, but more so in terms of the AFRP bars, what we're considering this deformability, since there's no clear yield point in how we kind of navigate that. We'll also look at the total dissipated energy of the column, and then this defined damage index, which is a combination of the cyclic dissipated energy as well as elastic energy. If we move on down and look at the local behavior, particularly of this system, which consists of the structural fuses all the way embedded down in a duct into the foundation, looking at the failure modes that we would see, be it the weld failure at the plates interface, yielding of the structural fuse itself, any fracture of the AFRP bars, which is not desirable, but definitely something that we're looking out for in these models. Then also looking at the contact stress at the column and footing interface as the column rocks. So for the inelastic column behavior, in terms of energy dissipation, we were able to, of course, come up with some ideal curve definitions as we try to tabulate what the results would be from these, from the numerical results. So for the idealized structural ductility for which we're defining it as the failure displacement, and H2 prime is the horizontal load equal to 80% of H1, H prime max. So basically taking the peak here and then coming up with these idealized curves so that we can then compute how much energy is being dissipated in terms of essentially the area under the curve. So we were also able to calculate, and just kind of from basic structural dynamics, as well as looking at various models recently produced by Osorio et al. 2014, of looking at the total dissipated energy to compute that. For the damage index that we're defining based on Osorio et al. 2014 combines the cyclic dissipated energy as well as the elastic energy to come up with an index to figure out how much damage we're seeing in the column. So definitely a lot of results that we got from the parametric study. So we can focus on column 5, 6, 7, and also 8. I know before I'd also mentioned column 4, which we know, and then also as we evolved, we noted that as we varied the longitudinal reinforcement ratio as well, and also looking at the various confinements, we're able to see that we were able to get pretty good peak loads. This is load versus displacement. But of course, as we shorten close out this tie spacing, we even went down as far as 2 inches. So dropping it from 5-inch spacing to about 2-inch spacing. So in tabulating all the results that I showed you before, in terms of column drift for the C4 column, we were getting about 5.7 drift compared with C7 and C8 for the AFRP columns. Also, we looked in terms of ductility and energy dissipation. We actually saw that we got a large amount of energy that was dissipated. But moreover, if we look at the damage index number, we had a lower damage index, meaning having the system to rock to dissipate energy was very advantageous, such that we're not focusing as much damage within the column, but allowing essentially the dissipators to yield and take on those stresses. So in terms of the local failure mechanics, as I mentioned before, we were able to see from the finite element model how much